Hi, I'm Brandy Heflin. I'm a personalized physics instructor and I help high school and college students feel confident and successful in learning physics. I'm here today to continue with part 2 of my mathematical modeling and data handling video series. In part 1, we talked about interpreting slopes and intercepts of linear relationships. And today, we're going to talk about additional graphical relationships and the process of linearization. While many of the data sets that we collect in an introductory physics lab will have a linear best fit, there are a handful of specific other graphical relationships and fits that will appear, namely quadratic, inverse, and inverse square. Quadratic relationships look like parabolas, top opening and side opening. And you might remember that a top opening parabola follows the basic equation, y equals x squared, while this side opening parabola is y equals the square root of x or y squared equals x. And while both quadratic and exponential equations have that same upward top opening curve, they are not the same relationship. So let's highlight some of the differences between them to help you understand better the data that you might see in a physics lab. So first, let me point out that we have shown here y equals e to the x, and then we also have, just in case it's hard to read from the bottom, in green we've got the function y equals 2 raised to the power of x, and down here in blue we have y equals x squared. So one key way that you can tell the difference between an exponential relationship and a quadratic relationship is that the exponential relationships blow up much more quickly. In other words, while x is still relatively small, the values for an exponential relationship get very large very quickly. And here's what I'm talking about. While x equals 4, our y equals x squared and y equals 2 to the x have values less than 20, but y equals e to the x has a value near 60. And then if we go up even further to, a small x equals 5, we have values for y equals 2 to the x and y equals x squared that are still under 40, while we've already, with e to the x, made it to close to 150. So again, exponential relationships and quadratic relationships will look similar for small values of x, but they blow up very, very quickly. And even when we take a closer look at that y equals 2 to the x and y equals x squared, same colors again, green is y equals 2 to the x, and I'll go ahead and write that for you. This one is the y equals 2 to the x. And down here in blue, we have y equals x squared. When we take a closer look at, a different range of x values, the difference becomes even more apparent. So up to about 5, you can see that our two functions look very similar to each other, our y equals 2 to the x and y equals x squared. But when we double our x values and make it up to x equals 10, and even in between that 5 to 10 range, you can see, y equals x squared at a value of 10 is 10 squared, which is just 100, while y equals 2 to the x at a value of 10, that's going to be y equals 2 to the 10th power. You can see that we've already made it up to greater than, actually I shouldn't say it that way, I should say greater than, I've got an eraser, hang on, there we go. We've made it up well over 1,000 with a value of x equals 10. So, we can always check if we're not sure when we have a data set. We can test the model that we think we have and plug in some larger values of x to see what we end up with to tell the difference between exponential and quadratic. Our next kind of relationship is the inverse relationship. That looks like a hyperbola. with an inverse relationship, neither the x-axis variable nor the y-axis variable will ever be equal to 0. And we have a couple different ways of describing this kind of function. The basic equation is y equals 1 over x, or another way would be that the product of the two, x times y rather, will be equal to some constant value. So it doesn't have to be equal to 1, but when you multiply them together, they'll be equal to a constant. And last but not least, we have inverse square relationships, which also look like hyperbolas, but with a few key differences. So the orange one on this plot is the inverse square, which first of all, what does that mean? It means that x and y are not just inverses, but x is actually squared. So what that means is, as our x values decrease for an inverse square relationship, the y values get bigger much more rapidly than for an inverse relationship. And on the other side of that, as x increases, you will notice that the inverse square relationship has much smaller values than the inverse relationship. So we say that the inverse square relationship approaches the axes much more quickly. So we've talked about a number of different kinds of relationships that are likely to appear in our introductory physics data. We know how to write the equation for a linear relationship, y equals mx plus b, where y is our dependent variable, m is the slope, x is the independent variable, and b is the y-intercept. Well, what happens if we have one of these other relationships we've just talked about? Well, this process called linearization uses the mathematical function unique to each graphical relationship to manipulate the original values in order to produce a new graph that's linear. So we're going to think about matching the shape of the graph to the mathematical function that's going to tell us what operations to do on our input values in order to generate output values such that we always end up with a straight line, a linear graph, because we know how to interpret linear graphs. Recall that a mathematical function has one output value for every input value. So you can think of a function as a magic box that we put our input value into, and we're going to do some stuff to it. We're going to do some mathematical operations, and then it's going to spit out an output value. We're going to use a simple example of a linear relationship because, again, those only involve multiplying, dividing, adding, and subtracting. So here I have a simple data set of x equals 0 through 5, and integers, that is, and we're going to multiply each input by 2 and then add 3. So when x equals 0, y equals 3. And when our input is 1, our output is 5. And when our input is 2, our output will be 7. And an output of, let's try 3. Jumping ahead of myself there. We'll get an output of 9, and an output of 4 yields, input of 4 yields an output of 11, and last but not least, multiplying 5 by 2 and adding 3 gives us 13 as our next value. And what we can do now is take a look at those final values put into their own little table and then plotted. So again, we have this notion of magic box that we do some mathematical operations to our input value and then spit out the output. And so during linearization, we're going to use the function suggested by the shape of the graph. Remember, we're going to have top-opening parabolas, side-opening parabolas, hyperbolas, to create a new magic box for our input values that produces the same output. But we're going to think of it a little differently. Instead of putting the input into the magic box, doing the operations, and then getting the output, we're going to think of it as doing the operation and then putting the input into the box to get our output, where the box is always going to make something that's linear, so that we've had this input that we've done some extra stuff to, and then when we put our input in the box, we're only ever going to multiply, divide, add, or subtract. Let's work through a few examples. So let's review quickly this idea of magic box for a simple quadratic function y equals x squared. So we'll have our input of x that goes in the box. The operation we're going to perform here is squaring to get our output. And this is going to set us up for linearizing a different quadratic function on the next slide. So when we square our first input of 0, we get an output of 0. And then 1 squared, of course, is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16, and 5 squared is 25. So here's our table of final values that we're going to plot, x and y, and then we see our top opening parabola, y equals x squared. So we're going to always remember when we see a top opening parabola that there's been a squaring of the x value, and then if we're linearizing, we've squared our x value, and then we're going to put it into this other magic box that's going to multiply or divide or perhaps add or subtract values. So it kind of uncomplicates, believe it or not, the mathematical operations that have been done. So here's our new top opening parabola graph and data. I've gone ahead and put on the graph that the function we're going to be working with is y equals 2x squared, and I'm setting you up with that to help explain the calculations that we're about to do. So here's the process. Since that top opening parabola shape suggests a quadratic relationship of y equals x squared, we're going to take our x values and we're going to square all of them and use that as the input for this other function that's going to generate something linear. So we had x values that were integers from 0 to 10. So on this table, we have a column that shows x squared values, 0, 1, 4, 9, 16, 25, and then we've gone on with 36, 49, 64, 81, and 100. So that's taking care of our operation suggested by the shape of the graph. Now we're going to take those values and put them into our other linearization magic box, where we're only going to, in this case, multiply by 2. So when we take 2 times 0, of course, boring, we get 0. When we take 2 times our input value of 1, we're going to get 2. And when we do 2 times 4, we'll get 8. And when we do 2 times our input of 9, we're going to get 18. And when we do 2 times our input of 16, we'll get 32. And when we do 2 times our new input of 25, we're going to get 50. And so we took our 6 and squared it to get 36, because that's the function suggested by the shape of the graph. And when we then multiply that by 2, we get 72. Feel free to pause this and go back and take a look at those values that were in our initial data table. And you're going to see that, when we take our x values and square them first, and then use that as input to multiply by 2, we're generating exactly the same values that we had in that first table. So that's partially because we chose a really simple function here to use as the example. And last but not least, when I take 2 times 100, I get 200. And so these are now the values that we're going to plot. So again, the process. We look at the shape of the graph. It tells us something about the mathematical function, the operations that were done on our input. We're going to do that core operation from the shape of the graph, in this case squaring, and then we're going to put into the linearization magic box where all all we're going to do is multiply by 2 in this case. And so we're then going to use our x squared inputs and our y outputs to create this new graph that's going to be a straight line. That shows up on the next slide. So it seems like a strange process, but it works. And notice what I've done here is I've put the x squared in brackets to describe the line on this graph because we took our original x values and squared them, and those were the inputs that got us this graph. And you can see in the data table too that every y value is just 2 times the value that's in the x column. So quadratic, top opening parabola at least, is a really nice simple one to start with to learn this process. So what about a side opening parabola? We're going to recall what I mentioned earlier, choosing a nice pretty color, that this graph describes the function of y equals the square root of x, which is going to be tougher to plot, not going to lie. So what we could do instead that's just as valid is y squared equals x. So in this case, we're actually going to be manipulating our y values instead of our x values when we go to make that plot that's linear. So recall here that we had y values that were the integers from 0 up through 10. So let's fill those in really, really quickly. And then let's talk about our y squared values. So our idea of our input and output is a little bit different here, but that's because we have this side opening parabola, and it's a lot harder to proceed with our mathematical modeling dealing with the square root than it is to just square that vertical axis variable. So our y squared value, when y is 0, and when it's 1, it's 1, and when it's 2, it's 4, and when y is 3, y squared is 9. And you don't need me to read all of these to you. And so I hope that you're noticing I am getting a column of values for y squared that is exactly identical to my input values for x. So we should get a straight line whose slope is equal to 1. And there we go. So check out our x versus y squared values that we'll look at for a graph on the next slide. And as promised, when we do our operation, this time on our y value, and then use our magic linearization box to get our output values, we now have ended up with a straight line whose slope is equal to 1. And again, because it was y squared that we used for this data set, I put those values that we've already done an operation on in brackets. So I've now given you a couple of data sets to try. You can use Microsoft Excel or Google Sheets or Vernier Graphical Analysis to give this a shot. You can feel free to pause the video and go put these values into whatever data analysis and calculation and graphing tool that you want to use, and see what you come up with. So you've got these values, make the graph, check the shape. What mathematical functional relationship is suggested by the shape of the graph? Then do the appropriate calculation based on the shape of the graph. Are you going to change x? Are you going to change y? I'll give you a hint. These two, you're going to change x. And then do your calculation and make your new plot with your manipulated data to get a straight line. And I've provided answers for both of these data sets after the Ways to Connect slide coming up. So one more time, a summary of linearization. The shape of a graph suggests a mathematical function, and that function determines what operation we're going to perform on our input value in order to have a linear function through our outputs. Then we're going to replot a graph using our manipulated values to get a linear graph that's easy to interpret. We already talked in our last video about how to do slope and intercepts. And if you haven't watched it yet, feel free to go check that one out too. So I hope you've enjoyed today's video. I know that this is a strange topic that you've probably never come across before, and not every physics class will do this, but learning how to do mathematical modeling of physics data is so important because every equation in physics that's important came out of some kind of experiment, some kind of real-world collection of data. So if you'd like to connect further, you can email me at brandyheflinphysics@gmail.com. You can check out my site, virtualphysicsofficehours.com. If you'd like to work one-on-one, click the red button that says Book a Needs Assessment, and we'll set up a short call to talk about your challenges, your struggles, your goals, and we'll set up a free first session. And you can also find me on Facebook. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time. So as promised, here are the answers to those two data sets from a few slides ago. The data set in the left-hand table was an inverse relationship, which recall suggests y equals 1 over x as our fundamental relationship. So you should take your x values and calculate 1 divided by x, and then plot 1 over x versus y, or y versus 1 over x. And in fact, what we will get is y equals 10 times 1 over x, or you could also write it as y equals 10 divided by x. And the data table on the right was an inverse square relationship. So that's suggesting that the fundamental relationship is y equals 1 over x squared. So we should square our x values and then take 1 divided by that, and then we will plot 1 divided by x squared versus y, and we will get y equals 2 times 1 over x squared, which we could also just write as y equals 2 over x squared.